So far we've looked at how a current running through a wire creates its magnetic field around it. Now imagine placing that inside a big magnet which also has a magnetic field. What's going to happen? That's what we're going to look into today. Let's start with a uniform magnetic field between two magnets. I'm going to add some field lines, like so. Things to notice. The field lines are straight. The field lines touch the surface. That means they never just finish in midair. The field lines leave the surface at 90 degrees. The field lines have a direction away from north towards south. The field lines, and this is important for today, the field lines are evenly spread out. Now, let's look at the wire by itself. Here's our wire with its circular field. You should be comfortable with the right-hand grip rule to get the direction. Let's place it inside a magnetic field now. Right, so now there are two magnetic fields. I want you to focus on how these fields will interact. We'll start by focusing here. The field from the big magnet is going left to right, and the field from the wire at this point is also going from left to right. They are going to add up to give a strong overall field. Now, focus over here. The field lines from the magnet are still left to right, of course, but now behind the wire, the field line from the wire are going from right to left. The field lines are opposing one another. What effect will this have? Have a think about it. Well, the field will cancel out at the back but be strong at the front. Let's switch to an overhead view so we can see it more clearly. Now we're looking down. The current is flowing towards you, so get your thumb out, right hand grip rule, put your fingers over the red circles. They should line on the circle with your fingers pointing the same way as the arrows. And your thumb should be pointing towards you. Now, you can see easily that we have a strong field here and a weak field here. How do we normally represent a strong field? If there's only one bar magnet, for example. So on a bar magnet, we show a strong field by having lots of field lines close together. Let me show you what it will look like. That's getting quite messy, so I'm going to sketch it again quickly. And there we have the field pattern. Now the clever bit. Notice how these field lines are very close together. This requires a lot of energy. Also, they are longer than they need to be. This also requires energy. So there's too much energy. What do you think will happen? What do you think? Well, the field lines will try to straighten and spread themselves out, but the field lines cannot cut through the copper, or at least they prefer not to. So they take the copper with them. Imagine these were elastic bands. They catapult the wire upwards. Is the motor effect. Motor means movement, and the current inside a magnetic field has created movement. It's not free because we have to supply a current, so we're putting in that energy. Now, working out which way it will go every time is slow, so we have Fleming's left-hand rule to help out. Okay, so get your left hand out. Let's try this. Your left hand, first finger field, so point your first finger in the direction of the field. That's left to right. Second finger current, point that towards you. Keep your first finger still. Thumb thrust. You find your thumb is pointing up the direction the copper wire is going in. If you follow that, you should be able to give these a try. The first 4 are not too bad, but you might have to think a bit for the last couple. And by the way, you already saw that a circle with a dot represents a current coming towards you. A circle with a cross means the current is going away from you. I like to think of an arrow with a cone tip. If the arrow is fired at you, so it's coming towards you, you will just see the cone and the tip. But if you fire the arrow, you'll see the cone and the feathers. And if there's no circle like 3 and 5 here, then that's representing the direction of the field, not the current. So that's the motor effect. We took a magnetic field created by a wire and a magnetic field created by a permanent magnet, and we combined them together to get movement. We still got to get something useful out of that, but we'll save that for another time. For now, I'm going to leave you with these problems, so have a good think over them and check with your teacher for the answers.